My aim in this lecture video is to show you a new physical quantity referred to as the magnetic dipole moment. And so you can see up in the left-hand corner that, right, that's what the title of this little talk is about. In the previous video, we got a result towards the end, this result. So what we have is we have this background magnetic field that's uniform, and it points from left to right, has some uniform strength. The strength I'm just denoting by capital B. It's up here in the expression. There's a current that's winding around in the sense that you can see here in the diagram over on the right side. And the current I'm describing with the capital letter I. The height of the rectangle is called L1, and the width of the rectangle is called L2. And you can see that L1 and L2 and the current I all show up in this expression multiplied. And then there is this angle. And the angle beta was from calculating torques. And you can see what that angle beta is in the diagram. So this, so you can see the red magnetic field lines. And then you see this diagonal black line. The diagonal black line is meant to just be this edge of the rectangle here, L1. So this is an L1, right? I drew the blue dot in the center because the torque that we calculated was actually the torque about this blue position that's midway along the length L1, right? I've got a force acting at the top of the current loop that's trying to bring it down, and a force acting at the bottom of the current loop that's trying to bring it up. And so this is a twist, and twists in physics, we call them torques, right? Twisting forces or twisting actions or something. Torque is not directly a force, but torque is related to a force acting at a distance from a pivot point. All right, so we have this expression, and you can see what the angle beta means. So the thing about the angle beta, it's going to be useful actually to define another angle alpha. So I'm going to define alpha to be this other angle, and you can see that if you were to take alpha and beta and you add them together, what you get is 180 degrees, right? So instead of writing it this way, I'm gonna do something. I'm gonna do this. I'm gonna take beta and solve for it. So it's 180 minus alpha. And I alluded to this in the previous video that there's something symmetric about the angle alpha and beta for the sine function. The symmetry is because alpha and beta are the same angle away from 90 degrees. Yeah, so that's a weird way to say, but what I was meaning by that comment is if I took the sine of beta, this is the same thing as the sine of 180 degrees minus alpha, right? And there's a trigonometric relationship that helps me expand the sine of this combination of angles. So it turns out it's the sine of 180 degrees times the cosine of negative alpha plus the sine of negative alpha times the cosine of 180 degrees. So this is called a double angle formula. And the reason I do this is because of the following. The sine of 180 degrees is 0. That's one of the points at which the sine function comes down and goes through the angle axis. So that means the first pair of factors, they just factor to 0, and yeah, so the only thing that counts is this other expression. And the cosine of 180 degrees is actually equal to -1, and the sine of negative alpha, right, the sine function is odd on its argument, so this is the negative of the sine of alpha. So if you put these things in, what you get is that the sine of beta is equal to the sine of alpha. And so the reason I do this is because I want to study this picture, but with a little bit of an augmentation. I'm going to augment this picture by identifying what's called the normal to the area. So this area, let me actually put it in purple. So the area here, remember I brought up in the previous lecture video that it was interesting that this torque formula doesn't depend on the lengths separately. It depends on them as the product, right? And this product shows up. So so this torque has something to do with the area enclosed by the current loop, right? So that's this area here. So I'm going to define an interesting vector. It's the normal to this area. So I'm going to imagine it emerging from, say, the center of this area, but I'm going to orient it according to a right-hand rule. So the right-hand rule, I'm going to try to draw a right hand. So here is a wrist, and for the right hand, this right here is the thumb, and then the thumb comes into the rest of the hand, and here is the right hand, the knuckle of the index finger and the index finger. This is the knuckle of the middle finger and the middle finger, and this is the knuckle of the ring finger and the knuckle of the pinky. So there is the pinky and the rest of the hand, right? And here is, so I hope you can see that this is a right hand, and I'm applying a rule with it. You can see that the right hand is indicating the way the current is flowing around the loop. Can you see that the current is flowing from the wrist through the knuckles, through the fingertips of the right hand, oriented this way? And the thumb points out the normal to the surface that I care about. Can you see that? Normal. So that's the normal I care about. And I'm going to designate it as the normal vector. And so in this drawing, the normal vector points perpendicular to the black line, and it points in this direction here. So if I look at this normal vector, though, I can say something pretty interesting. It turns out that this normal vector, let me think a second. I should have thought this through just a little bit beforehand. Yeah, okay, so here's, it's a little bit complicated. What I'm going to tell you is that if you follow the angles of these triangles, right, there's actually a lot of triangles. There's the, so let me redraw the diagram here. So you see this, like, there's a black edge here. It looks like hypotenuse, or actually that's not a hypotenuse. This blue edge labels a hypotenuse direction, and the purple edge is a side of a triangle, and the black edge is a side of another triangle. So let me try to draw that, and I'll draw it here so we can see the diagram at the same time. So this purple line, there is a horizontal red line, right? That's the direction of the magnetic field. You see the horizontal red line? Then there is a black line. And the black line is this diagonal line, which is actually perpendicular to the purple, right? And then there's this blue line that is also an interesting direction to keep track of. And you see this triangle I built. So it's got the normal direction, this purple. It's got the black, which is the direction of the current flow. It's got the blue, which is the direction of the force. And it's got the red, which is the direction of the magnetic field. And I've labeled an angle called alpha. And that angle is right here. Okay, so the interesting thing is, right, so this is a right angle. And actually also this is a right angle. Can you see there's a couple of right angles? And I've got multiple triangles. So the interesting thing about this is this angle alpha plus this angle over here plus 90 is going to add up to 180. And so what that means is that this angle right here is also alpha. So I'm going to go and pick it out for you. It's this angle and this angle is also alpha, right? You can follow the straight lines and the angles and the triangles, and you can discover which angles are the same. It's an exercise of a piece of paper, and it's worth doing for yourself every step, right? I think you should do this. So anyways, so that angle is also alpha right there. So all this is to say is there's something really important about this purple normal direction. And what I'm going to define is an area vector. And you might recall this actually. There is an area vector that's equal to the area of the enclosed area by the current loop, right? The purple area. So that's this multiplied by that normal direction, where the normal direction is defined according to a right-hand rule, right? Where I described using this right-hand rule to define the direction. The right-hand rule was important because actually, if you think about it, there's two directions that are perpendicular to the surface. There is also this opposite direction, right? This is the opposite of this. I need to choose one, and I'm going to choose based on a right-hand rule. So the answer is not the black arrow. The answer is the purple arrow, right? It orients the surface, just like in Gauss's law. Okay, so all right, so we have this thing. It's called the area vector. And if you look at the purple area up here, it's just L1 times L2. It's just the area enclosed by the current loop, right? And then, so what I want to convert this expression to is, if you look at this expression for the torque, let me rewrite it down here. The net torque was equal to I, L1, L2. Is that all? Yeah. And then B, and then the sine of beta, right? Where we had this old angle, but I showed you that actually the sine of beta and the sine of alpha share the same value. So I'm going to start talking in terms of alpha. So the net torque is I, and then L1, L2, B sine alpha instead. And if I look at this, and I look at this, and I look at this, what this looks like is, if I was to define this thing as a vector mu, right, where mu equals the current times the area vector, right, where the area vector, I defined it here, it's got the normal direction that's defined by the right-hand rule. So I define this thing called the dipole moment. It kind of doesn't matter what you call it, but I'm going to name it this. I've got the B vector, right? It's sort of here. The torque has this sine of alpha. It's the sine of the angle, actually, that's between the magnetic field direction and this strange thing called the magnetic dipole moment direction. And so you can end up rewriting the net torque on the current loop as simply mu cross B. So this turns out to be an extremely useful way to talk about how current loops interact with magnetic fields. And yeah, specifically we derive this for a uniform magnetic field, but I'm just going to put magnetic fields. It's actually true. Well, I won't go there. So this is an important relationship. And an important aspect of learning how to use this thing is being able to actually define the magnetic dipole moment. So I have just a little bit of an update on how to, so I've described this as I times A, like this, where the area vector is defined with the right-hand rule. But there is a little bit of an extra definition. I'm going to put a factor n, where n equals the number of windings. And the idea is you could imagine taking a piece of wire and coiling it up. And you know it's got to be a cycle. So here is that coil. And you don't tend to think of the thing as being spread out. What you do is you imagine making a current loop that's actually flat. It's just got lots and lots of windings, like that. So you might say that it was wound n times, right? N windings. And all that means is if you were to look at a section of the wire, right? If you just look right there, what you're going to see is lots of wires, right? I just drew, I don't know, 7 or 8 of them. Let's say n equals to 8. And each wire carries the same current, I, right? So 1, 2, 3, 4, 5, 6, 7, 8. Let's pretend there are 8 wires there. And if each one carries current I, right, then the total current that's being carried through this leg of the coil is 8 times the current of each wire, right? So we can say that the magnetic dipole moment is increased if you have multiple windings. And it's increased simply by the factor, or just the number of windings as a factor. Okay. So notice something. Let me now redraw the problem a little bit. So I'm going to put a magnetic field, and I'll just draw it the same as before. It's towards the right. And before I draw my next drawing, or actually no, I'm going to go ahead and draw it. So here is a current loop. I'm going to draw it as a circle, right? And we could say that the number of windings is 4 and the radius is, say, 1 centimeter, something like that, right? So I know I derived everything for rectangles, but the truth is this actually, this formula for the magnetic dipole moment, it works for a flat any shape, including a circle. So the area of this circle is just pi r squared, right? So you can just plug in that. And then let's use the right-hand rule, but this time, let's say the current actually is winding in this direction. So that's the direction sort of out of the page at U. So it goes around and goes into the page here, right? And is heading upwards here. Right, so it's winding that way. So if you use the right-hand rule, the normal vector is this. So that's the area vector. And that's also the direction of the magnetic dipole moment. So from the side, if I draw this picture one more time, so if I just imagine looking at this really just from the side, so I've got the magnetic field, and I've got this current loop. So from the side, it's oriented this way. Its magnetic dipole moment arrow points that way. And what you see is that the torque tends to realign the magnetic dipole moment vector with the magnetic field. That is, it's sort of like a little compass needle. If you take the tip of the compass needle and you try to rotate it away, you are fighting the background magnetic field, and if you let go of it, it's going to snap back, and it's actually going to snap all the way back to here, right? And if this current is say on a pivot so it can rotate, what it's going to do is rotate past, because it has a moment of inertia, right? It's got rotational inertia. So it just twists through the equilibrium to the other side, and it'll twist back and forth. So you can set up oscillations, right? If your pivot point has friction, then the oscillations are slowly going to die away as energy is converted to heat through friction at the pivot, right? But the point is the torque by the background magnetic field tends to realign mu with the magnetic field. It tries to point it in the same direction. In our example up here, if this was the current loop, can you see how different our mu vector, this is actually the magnetic dipole moment vector direction as well, it's been rotated almost 180 degrees away from its equilibrium position. So if you let go of this thing, it would collect up a whole bunch of rotational kinetic energy until it rotated all the way to pointing in alignment. And if there is no friction, right, or if there's not a lot of friction, it just like keeps on going to some other angle on the other side, and then comes back, and then goes forward again, and back, forward, and slowly you lose the oscillation amplitude. You lose that oscillation energy to friction, to heating. All right. So, so this actually has somewhat of an energy component to talk about as well. And we can define, right, here's a useful definition for the potential energy. And it's simply equal to, so where the torque was mu cross B, sorry to wind back up here, where the torque is mu cross B, the potential energy is got to do more with mu dot B. But it's not mu dot B, it's minus mu dot B. And the idea is when mu is parallel to B, we should call this the minimum of energy, right? Because when mu is parallel to B, that means that the B field and the mu vector are in alignment, right? That's the minimum of energy. This is the equilibrium. You get more and more energy if you rotate the mu vector to point at an angle with respect to the background magnetic field, right? And so we would say actually that if we were able, to cause the magnetic dipole moment to actually point backwards, then the angle between the magnetic field and the dipole moment is 180 degrees. And this has, right, if you take the dot product between two vectors, so let's say A and a vector B, which is the opposite direction, the dot product between oppositely directed vectors is negative, but we want it to have the maximum positive potential energy. So what we do is we stick in this minus sign, and so when mu is backwards to B, you get this extra minus sign, and the potential is actually positive. It's actually maximized, right? So this is a useful definition for a potential energy. associated with the orientation of a magnetic dipole in a background magnetic field. All right.